Welcome to the Electrical Basics video. I'll be covering Ohm's law and kind of how it applies to FRC. We'll be looking at voltage, current, resistance, and the inverse of resistance, which is conductivity, and we'll have a couple of examples with batteries and a little bit of power distribution. So first is Ohm's law, which says voltage equals current times resistance. And over here you can see the abbreviations and units and symbols for all that. So volts is V, current, we run out of a lot of letters in electrical engineering. So current is abbreviated as the capital letter I. Its unit is amperes, which has a symbol of A. Resistance is R. Its units is ohms. And its symbol is the capital omega. And this wheel here is a really quick diagram to show all the relationships between voltage, resistance, current, and power. Some of the common ones here, V equals IR. And if you do a little bit of algebra, you can switch that around. So say you have voltage and resistance, you can find the current. Or if you only have voltage and current, you can find the resistance. Some that we'll be using later are power in watts equals I squared times resistance, so current squared times resistance, and power equals voltage times current. We use this one a lot. So what is voltage? Voltage is the measure of electrical potential. So if you look at this atom here, the atom is made up of electrons, neutrons, protons, and the neutron or protons make up the nucleus, which is the middle part. So those electrons are somewhat free to move around between atoms. So you have atoms all next to each other, and if you put a little bit of energy into that system, you can get those electrons to move from one atom to another. Those atoms like to be in a certain amount. So a copper atom, for instance, will have so many electrons that it likes to have in its atom, but it can have more or less, and that's where we get voltage. So if you strip away some of those electrons and you move them from one side to the other, kind of separate them, now there's a surplus of electrons or negatively charged particles. I'm using electrons kind of generically. Charged particle is probably more accurate because there are more than just electrons that can cause a voltage or carry power. So yeah, we have more electrons over here and we have a lack of electrons over here. So you're left with just the positive protons, and because of that separation, there is a potential. So all of these electrons would like to be over here to keep everything balanced, but we added some energy into the system, we charged that battery, and they are separated. So if you have more electrons on one side and a lack of electrons on the other, and you make that number even bigger, you'll get a higher potential. Now that potential is the potential to do work. So the higher the voltage, the more work you can do. That's why on a dead battery that's like 11 point something volts, you're not going to get as much work out of a battery that's at 13.2, a fully charged battery. So now we have current, which is the flow of those electrons. It's measured in amperes, as we said earlier. 1 amp is equal to 6.24 times 10 to the 18 electrons per second. So if you take one spot and you count all of the electrons that go past, if you have 1 amp, you'll have 6.2 times 10 to the 18th electrons moving. Now that is a weird number. That comes from a guy named Coulomb. Coulomb has his own laws, and they're pretty cool. You should go look them up. C-O-U-L-O-M-B. It's a weird word to spell. Now, when we look at current and we use it in math, we're looking at the flow of electrons from the positive side through our wires, through some type of load like a motor or a light bulb, something that's going to use that power. So we're watching the electrons flow from the positive side through that load and back to the negative side. That's the conventional way that we look at it and the direction that we have math working, but that's not actually what's physically happening. If you remember the previous slide, we said all of those electrons are on the negative side. They're all built up there, and they want to be on the positive side to meet all of those protons in the atoms and make everything happy again. So the electrons are actually flowing around the other direction. This is because Ben Franklin a long time ago didn't know this, so he set up this convention that said, oh, well, everything must go from positive to negative. And that's the way that we do our math today, but in reality, the charge carriers are moving from negative to positive. Now we have resistance. Resistance is a component of impedance. Impedance is really just things that can affect your charge carriers. It can affect your voltage, your current, a whole bunch of things. And there's three main components that can affect that. You have resistors, which are shown there on the right. You have capacitors and inductors, and I'll talk about those in another video. But resistance is really just limiting how many electrons or how many charge carriers can get from one spot to another. And they do take up a little bit of power, so it will steal some of those electrons or some of that energy going through the wire, and it'll turn it into heat. So we don't really use this anymore. This is the color coding chart. If you look at a resistor, you'll see a bunch of colors, and it tells you what the value of the resistor is. Now, unless you're really good at this and just memorize the chart, it's almost always faster to grab a multimeter and just measure it. And I will go over multimeters in another video. But let's use this 4-band as an example. We have a brown, red, and green. So if we go look at our chart, we have brown, which is 1, red is 2, and then this green guy is our multiplier. So we have 1 times 10 to the 5th, or 100,000. This is green one. So that gives us 1,200 kiloohms. So it's 1,200 times 10 to the 3 if we use engineering notation. And there's our little symbol of ohms, and that K is the prefix, meaning times 10 to the 3rd or times 1,000. And then we have this little gold band here. This is our tolerance band. So if we go look right here, it says plus or minus 5%. So 12 kiloohms plus or minus 5%. The resistor is supposed to be 12 kiloohms, but it might be 5% higher or 5% lower. So if you need a very specific value, you want a 1% or a 0.1%, but for all of our cases, a 5% or a 10% is okay. You'll see these at the end of a CAN bus. They're called a terminating resistor. Their value is 120 ohms, and normally they're a 10%. So 10% of 120 is 12. So it could be 12 ohms higher or 12 ohms lower. Doesn't really matter for the terminating resistor of a CAN bus. So 10% in our case is just fine. So now we have conductance. That is the inverse of resistance. So resistance is slowing down or limiting the amount of charge carriers that we can pass through something. So if you have a high resistance, things aren't going to flow very well, like a block of wood or your body or something in the mega ohms range, like millions of ohms. But for a wire that has a very small amount of resistance, and I'll show you an example later, you might actually talk about it in terms of conductance or 1 over resistance. Conductance is labeled as G here, that's its symbol, because we keep running out of letters, so we're just using random ones. But if you know the voltage and the current going through that wire, you can calculate the conductance. And then from there, you can calculate the resistance of the wire. So if you want to in lab, we can do a little bit of measurement. We can figure out approximately the resistance of that wire for a given length. Conductance is normally given in terms of length because as you add more wire, you have more physical stuff for those charge carriers to get through. And the more stuff you have to get through, the more you're going to be limited because you're always going to have a little bit of resistance in life. Okay, so here's that example. A common thing to look at is 6-gauge versus 4-gauge wire for our batteries. Turns out 6-gauge is just fine. If you look here, this is the number of ohms per foot. This is 1 foot, 2 foot, 3 foot, 4 foot. And I just did that because it made my math easy to make a nice chart on the next page. But you can see here that a 6-gauge wire per foot has 0.0004 ohms. That's almost nothing. So on this chart, we can see the voltage loss in a cable. Remember I said it, a resistor, much like a wire, everything acts like a resistor. You're going to lose a little bit of power. Some of it's going to be lost being absorbing some of those charge carriers, and they turn into heat. That's why you want a lower resistance when you're doing power transfer, big power transfer, like from the battery to the rest of the robot. The robot's limited to like 120 amps, so we're going to look right here. And our best case is the 4-gauge wire. So that's more wire, it's a thicker wire at 1 foot. So that's the shortest length that we're looking at here with the biggest wire. There's more surface area for all of those electrons or charge carriers to pass through. That makes it a little bit easier for all those to get through. So here we're losing like 0.03 volts right there. So over a 1 foot length of cable, you're not losing very much. And our worst case here is the 6-gauge at 4 feet. So you have a little bit smaller wire at 4 times the distance, carrying the same amount of power. So this, at this point, this is the same amount of power, same amount of current, assuming the same voltage. And you can see we're losing way more, almost 10 times the amount of voltage. But 0.2 volts in the grand scheme of things, you're not really going to notice it in the course of a match. As long as your battery's charged, you won't notice the difference. Now, this was done using Ohm's law, or V equals IR, and you can see all of those here. I'm assuming a 12-volt battery in my calculations, but you have amps, and then you have the resistance of the cable, and that's given per cable. That was all those numbers in the previous slide. And this is the voltage drop. So, little example of how you can use that. And this is the power lost in that cable. So this is current squared time over resistance, or times resistance, whatever that chart said. And you can see how many watts are lost in the cable. You can actually calculate how hot that cable is going to get over a period of time using this calculation. So again, looking at 120 amps, 125 amps, our best case is still the 4-gauge wire at 1 foot. You're losing about 5 watts, not a whole lot. But our worst case is the 6-gauge wire at 4 feet. You're losing about 25 watts, 5 times the amount. So at some point, if you're doing really high current, like way out over here, 250 amps, you might consider using 4-gauge wire. But over here, for our purposes, 6-gauge is just fine. This is a good way to compare and contrast wires and kind of double check what you need to use. So this is our battery that we use. It is a 12-volt nominal. That means when it's kind of charged but not all the way dead, this is where it likes to sit. So a fully charged battery is 13.2 volts approximately, and then you don't really want to run them any lower or discharge them any lower than 11.2 volts. Lead acid batteries, the chemistry inside of them, they don't like to be discharged that much, so we try and stay in that 2-volt range. If you go any lower than that, it's called deep cycling, and it will reduce the life of your battery. So here you can see the capacity is given in amp hours. So 0.9 amps, it's about 1 amp. Let's just use that for our math. And then they're taking a fully charged battery, so assuming about 13.2, they're discharging it down to 10.5. So a lot further, about 0.7 of a volt further than we would, but we'll use this for our math anyway. So 18 amp hours. So for our example, let's say that our robot is using 90 amps continuous to power the drive motors, whatever mechanisms you have, pneumatics, lights, all the stuff. And you have a 2.5 minute match. Is this battery going to provide enough power? Does it have enough capacity to last the entire match? Well, let's find out. We have a 12-volt nominal, and we have 18 amp hours. So that's a little bit tricky because I didn't have that in my chart earlier. So we have volts and amps and time. And we want to check if this battery with this much capacity will last that 2.5 minute match. If you want to, you can pause, try and do a little bit of math, see if you can figure out how many minutes this battery will last. And I'll show you in a second. Okay, so this is the math, and I'm doing it kind of quick and dirty. But if you have an 18 amp hour battery divided by 90 amps, that leaves you with time because the amps cancel. So now you have 0.2 hours, but we want that in minutes. So we're going to multiply 0.2 hours times 60 minutes. That gives you 12 minutes of time. But remember, that is assuming that you're going from a 13.2 volt fully charged battery down to 10.9. That's where this capacity number comes from. But we know we're not going down this far. Actually, it's 10.5. I made a mistake. We know we're not discharging it that far. So this number, you're not actually going to get 12 minutes. You might get half of that, 6-7 minutes, until your battery is down to 11.3, 11.2 volts, and it's time to change. So yes, this will work just fine for our match. It might even work for 2, but you may not be as good. So real quickly, this is the big block diagram of how the robot is set up. So you have the battery down here, and it flows through this thermal disconnect, which is our main breaker. So if you pull too much power, if you have too much current, too many amps flowing through here, it will get real hot inside and it will pop open. If that happens, you lose all connection because your battery needs to be a closed circuit. So it needs to go all the way from the positive through all of your stuff and back to the negative. So if this opens, you have no power. So the power distribution, you have your main battery coming in here, and then all of your motors and extra stuff come out of the power distribution panel. So that was a very quick explanation of a whole lot of things. I encourage you to go back through the video, write down some questions, come back and ask me, look them up for yourself. Wikipedia has some really good examples, really good explanations on things, a lot of history. And just as a reminder, I did a lot of very quick and dirty math, so be aware of that. Also, none of these pictures and diagrams are mine. I'm borrowing them from a whole bunch of people on the internet.